Okay, hello again. Again, in the interests of shaking off the rust from a couple of weeks of maybe not doing linear algebra, I want to talk about that exercise of how to prove if a given vector belongs to the span of some other vectors. So the last video we talked about how to prove a set of vectors are linearly independent. Now we're talking about whether some vector belongs to the span of the other vectors. I think you can see, if you remember the definition of a basis, as a linearly independent set that spans the space. That's when you have a basis of the space. That you need to check those two things, right? So, but let me start with somebody just hands you some fixed vectors and then there's this other vector and they say, does that vector belong to the span of these others? The typical test question. And also to help you get back into the groove of things. All right, so how to prove if a given vector W belongs to the span of some other vectors. So how to prove if a given vector W belongs to the span of some other vectors, V1 through Vp. Okay, that's what we're going to talk about here. Okay, again, how to get started on all these things is make sure you know your definitions. What does it mean to say, well, what is the span of a set of vectors? It's the set of all linear combinations of those vectors, right? So therefore, what we're really asking here is, can we prove that W can be written as a linear combination of those vectors? So W belongs to the span of a set of vectors, which I'm going to shorten this name by writing 1 through P. That's the same thing as writing this, right? We're saying W belongs to the span. Remember, by the definition, that's equivalent to saying that there exists constants in the underlying field, in the scalar field. So there exists constants Ci, I going from 1 to P, such that you can rewrite W, another pin there, you can rewrite W as a linear combination with those constants on the VI's, I equaling 1 to P. That's the definition. So we try to prove we can find these Ci. Okay, well, that is a vector equation, right? So it has an equivalent matrix equation. Let's see if I've got a pin for that part of the board. Let's try this. Okay, so it's got an equivalent matrix equation. What would that look like? Well, let's see. Maybe we should write that out in a little more detail so that it's immediately obvious how to rewrite it as a vector equation. Right, that's a vector equation. In other words, I'm writing here C1 V1 plus C2 V2 plus, so I'm just expanding the summation notation, CP VP is equal to the W vector. And in the process of this, when you're looking at this, you think, you know, if W doesn't have the right size that they're compared to the VI, then of course you couldn't write such a linear combination, right? So you might be able to get done with the problem sooner, thinking that. This vector equation is equivalent to this matrix equation. I'm hoping you remember this. That if you make the columns V1, V2 through Vp, and you multiply them by C1, C2, Cp in a column vector, that's the same thing as this. So that's the equivalent matrix equation, right? Well, that's equivalent to an augmented matrix. That's going to have V1, V2, VP, the set of vectors that we're wondering if their span contains that vector W. So if there exist scalars that make this true, then this equation, matrix equation, has a solution. Looks like a bunch of CI. And this augmented matrix has a solution. Looks like a bunch of CI, right? All right, let's look at an example. Example 1. Okay, so example 1, we're going to try here. Somebody queries, does this column vector 0, 1, minus 1, does that belong to the span of these vectors? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I've chosen these numbers to convey that it's some arbitrary vectors, right? Just pick some other vector in 3 space. All right, so let's say that's the question. Does this vector belong to the span of those? So the answer, that's a question. Once you stop the video, go off and try and answer it using these ideas. Come back and see if your result looks like this as we proceed, or is logically equivalent, right? And also, I'm demonstrating, as usual, how to write down your answers to convey that you know definitions and that you're showing your work as economically as possible. So that's same rules apply in that if I'm demonstrating to you how to do a problem on the board, movie, I'm expecting you to be able to produce similar work. All right, so let's call this vector W, and let's call these vectors V1, V2, and V3. So if somebody asks me this, I remember the definition. By definition, this is what I would write to demonstrate I know these things. This is what you'll be doing. By definition, W belongs to the span of the VI, I equaling 1 through 3. That's what my P is here. There's 3 of these vectors. W belongs to them if and only if there exists C1, C2, C3 such that C1 times V1 plus C2 times V2 plus C3 times V3 is equal to W. Right. So it shows you understand the definition of span, of linear combination. Okay. That's a vector equation. It has an equivalent matrix equation, which looks like V1, V2, V3. Yes? When you're showing your work, you're kind of repeating the theory. Yeah, that's true. Showing what you know and organizing your thoughts, making sure there's no logical gaps in your presentation when you're answering. It's equivalent to the matrix equation that looks like this, where W is written as a column vector there. So if these exist, then this matrix equation has a solution. It looks like those CI, and equivalently so does this augmented matrix. Well, now I'm going to start putting in these particular numbers. So remember, writing V1 here, I'm saying it's the first column vector, so let's put those in. 1, 2, 3, 4, 5, 6, 7, 8, 9, bar, what's W? 1, 0, minus 1. It's equivalent to saying this has a solution. A bunch of CI that are real numbers. Run off to RREF, come back. You should go off and do that. Stop the video, go back and do that, and end the problem. Okay? Do it on your own. From here, now come back. All right, so you come back and you've got an RREF that looks like this. Okay. What does that mean? Well, again, we went from a vector equation to a matrix equation to an augmented matrix. So let's go from augmented matrix to matrix equation to vector equation. So that's equivalent to saying what? Well, that this matrix 1, 0, minus 1, 0, 1, 2, 0, 0, 0, if it's multiplied by C1, C2, C3, that you will get 0, 0, 0 vector, right? What is that equivalent to? That matrix equation is equivalent to system of equations. What system of equations is that? Excuse me while I try to adjust this, hopefully. Yeah, there we go. What's equivalent to that? Writing, well, multiply that by that. What do you get? C1 minus C3 is equal to 0. That's your first equation. C2 plus 2 C3s is equal to 0. And last but not least, 0 is equal to 0. So what does that give us? C1 is equal to C3. C2 is equal to minus 2C3. And that's a true statement, and nothing said about C3, nothing specific. So C3 is any real number. All right? So we were asking, does that system of equations have, does that matrix equation have a solution? Yeah, it's got infinitely many. Just to make your point, though, let's pick one particular one. So let's choose, choosing C3, say, equal to 1, then C1 will be equal to 1, and C2 will be equal to minus 2 times 1, or just minus 2. In what situation? We'll go back to the original. Look what you were saying over here. That we were looking for CI such that a linear combination of those three vectors using those CI adds up to W. Demonstrate that. Plug them in, plug these C's that you got your hands on, specific set, into that. So in other words, all that above implies this, that 1 times V1, 1, 2, 3, plus 1 times V2, 4, 5, 6, minus 2 of these 7, 8, 9s will be equal to our W vector. Yes, sorry. Let's see now. Okay, what was our W vector? It was 1, 0, minus 1. Okay, write that down and double check. Is that true? Is 1 plus 4 minus 14 equal to 1? No, that's not true. What happened here? Let's see. Might have been the case that when I ran that through RREF, maybe I put zeros in here. Let's double check. So you stop the video and you double check while I'm double checking. Okay? So is this really the result? Let's go back. I have a feeling it's not. Well, let's see. So second function matrix, I need a 3 by 4 here, right? And I think this one was this example. Let's see if that's right. 1471. Yep, there it is. 2, 5. That's an 8. 3, 6. All right. So if I send, that's my matrix B. If I send that into RREF. All right. I'm grabbing. Maybe I should be showing this. I don't know if you guys can see this. Does that at all work? You need to send me an email if you're having trouble making the graphing calculator work, okay? Because then I could do a particular type of setup that works for showing the graphing calculator. Yeah, I don't have a projector here like I do at school, do I? All right, so that was the matrix B in my calculator. Yep. So I shouldn't have been getting those zeros there, so I do have some corrections to make. Got a little ahead of myself with technology, and I was trying to do the example before I worked the movie. All right, so that's my excuse. Yeah, okay. So what I should have written there is this: 0, 1, 0, -1, -5/3, 1, 2, 2/3, and 0. Yes. That's what goes in here. -5/3, 2/3, and a 0 here. So coming over here now, let's see. What does that say? So C1 minus C3 is equal to a -5/3. And 1 times C2 plus 2 times C3 is equal to 2/3. But we still have 0 is equal to 0, so that's good news. We still have a solution. Or sorry, we have a consistent system. Excuse me. So what do I have here? C1 will be equal to C3 minus 5/3. C2 will be equal to minus 2C3 plus 2/3. And again, C3 could be any real number. So let's see. If I choose some nicer numbers here, let's say I choose C3. What am I going to be doing with C3? I'm going to be subtracting 5/3 from it. And this one I'm going to be doubling it. So why don't we make that, yeah, let's just make that 6/3 or 2, right? So then what does C1 become? C1 will be equal to 6/3 minus 5/3, or 1/3. C2 will be equal to -2 times 6/3 plus 2/3. What's that? -12/3 plus 2/3 is a -10/3. And that's my C2. And again, C3 was equal to 2. So I need to just change these numbers here. So my C3 is equal to a 2. My C2 is equal to a -10/3. And my C1 is equal to a 1/3. All right. So now I do have a linear combination of those 3 vectors, adding up to 1, 0, -1. Even though the numbers were nastier looking, than I had thought, and now they're correct. Well, let's double check. Is it true that 1/3 minus 40/3 plus 14 thirds, 14 times 3, 2 and 1, 42 thirds. So 1/3 minus 40 thirds, 1/3 minus 40 thirds plus 42 thirds. What does that equal? 42 minus 40 is 2/3 plus 1/3. That equals 3/3. And yes, that's equal to 1. Just checking at least the first line. Okay, great. What have we got? Go back to your original setup. Does this belong to the span of those? In other words, can we write that 1, 0, -1 as a linear combination of the VI? Yes. So the answer is yes. W belongs to the span of the VI. Because why? Because this is W, and we've just written it as a linear combination. 1/3 V1 plus minus 10/3 V2 plus 2 times V3 to get W. Okay, so it belongs, let's get you in that last frame. Sorry about that. So what have we shown? Yes, W belongs to the span right here, because here it is written as a linear combination of those three vectors. Okay.